In this section, we move beyond exponentials and we talk about logarithms. Now, logarithms traditionally have a base 10, but we'll also be talking about special logarithms which have a base e. So, logarithmic and exponential functions are very closely related. They are related because they're known to each other as being inverses of each other. Now, in order to be an inverse of each other, there's three characteristics that fit for inverses. What it means is that the x and y values have been switched in the equation and then solved for y, or the x and y values have been switched in the table, or they're reflected over the line y equals x. So we're going to do a recall for exponential functions, whether they're increasing or decreasing. We're going to sketch these two exponential functions, and then we're going to sketch their inverses. Then we're going to determine the following for each of them. So first off, we have 2 to the power of x. Well, 2 to the power of x is really nice and easy to do, because we can just set up a table. -2, -1, 0, 1, 2. 2 to the power of -2. So I'm just going to do that up here. Well, that means that negative, I'm going to take the reciprocal, take to the power of 2, which means we'd actually be at 1/4. Likewise, using the same kind of procedure, 2 to the power of -1, oh, sorry, wasn't going to write that there. 2 to the power of -1 means taking the reciprocal and putting it to the power of 1, or in other words, 1/2. 2 to the power of 0 is 1, 2 to the power of 1 is 2, and 2 to the power of 2 is 4. So if we sketch this, at -2, we'd be at 1/4. At -1, we'd be at 1/2. 0, 1, 1, 2, and 2, 4. Now I know that my exponentials, ignore that little updraft, but it would look like this. Likewise, we can do the same kind of procedure for this one. So if we have points x, y, and we use -2, -1, 0, 1, and 2, 1/4 to the power of -2 means taking the reciprocal of it, which means 4 to the power of 2, which means 16. 1/4 to the power of -1 means taking the reciprocal to the power of 1, because taking that reciprocal removes that negative, we'd have 4. 1/4 to the power of 0 is 1. 1/4 to the power of 1 is 1/4, and then we'd have 1/16. So same work. Now, of course, 16 would be way up here. We could put the point, but that would be a rough approximation. I know that actually probably be a little bit higher. But we can sketch our other points. -1, 4, 0, 1, 1, 1/4, and 2, 1/16. Obviously, we can tell that this first graph would be an increasing exponential because our base is 2. In this one, our base is 1/4, which means we know that it would be a decreasing exponential. I am just going to fix that part in the middle, because it does have to go through 4, it does have to go through 1. Make that look a little bit nicer. There we go. So this one, as I stated, is an increasing graph. This one is a decreasing graph. So what we're going to do is we're going to sketch the inverses, which means we're going to be taking the logarithm of it. So in order to take the exponential and turn it into the logarithm, we take the x and y values, and switch them in the equation. Well, that kind of procedure isn't necessarily part of the Foundation 30, but it's not bad to do. So what we do is we switch the x and y. And what overall happens is that the y and the x would change, and our logarithm would be this. Y would be log base 2 of x. The same kind of thing happens here. So x would equal 1/4 to the power of y. And the equation would then become log base 1/4 of x. Now the full procedure in order to do this is more of a pre-calc concept. And I usually try and do something like this when I go into extra instruction in Foundations 30. But what we can do, so we've done the equation, we can take all of our points, where is it? All the points x and y, and switch them on the table, which means instead of it being x, y, we are just going to change these to y and x. So if our x was 1/4, our y value would be -2. When our x is 1/2, our y is -1. X is 1, y is 0. The point 2,1 and the point 4,2. 4,2. This graph, by connecting the dots, actually looks like this. On this one, again, we switch them. So 1/16 2 would be like right there. 1/4 1, 1 0, 4 -1, and 16 -2. Well, what that means is our graph is going to look like this. Would run along the y-axis. I'm trying to be as careful as I possibly can. And there will be our graph. Now the other way of doing it is simply reflecting over line y equals x. Our line y equals x is that line. So let's look at our characteristics. We're going to talk about the x and y intercept for each, and behavior, domain, and range. So our first one, y is going to be equal to 2x, and then we're going to do the y is equal to log base 2 of x. So the first thing is our x-intercept. So on our exponential, we have no x-intercept. The x-intercept, there is none. But on our logarithm, our x-intercept is 1. On the exponential, our y-intercept is 1. But with logarithms, they actually do not cross the y-axis. They stay just strictly on the right of the y-axis. which means there is no y-intercept. C, oh, sorry, they're not A, B, C. I'll change those right now. They're I's. So I, and behavior. Well, for the exponential, it's going from quadrant 2 to quadrant 1. On the logarithms, we see that's actually going from quadrant 4 up to quadrant 1. Because we still read from left to right, and it's starting down in quadrant 4. And then we talk about the domain and the range. So I'm just going to put my letters down. Yeah, domain and range. So our domain on the exponential is all real numbers. Our domain on the logarithms, it's only our x values that are greater than 0. Now it's still all real numbers, but it's only the x's that are still greater than 0. Our range on the exponential, it's only our y values that are greater than 0. Y is still an element of real numbers. And our range on the logarithms, on this one, we can see it's going down, and this arrow still means it's going to keep on going up, which means it's actually y being an element of the real numbers. It's all possible y values. So hopefully you can start seeing a little bit of pattern here. In each of these, because they're inverses, the x's and y's had to switch. Well, if we look at it here, on the exponential, there's no x-intercept. On the logarithm, there's no y-intercept. The y-intercept on the exponential is 1. The x-intercept on the logarithm is 1. Now the end behavior is a little bit different, and I'll talk about that in a second as well. But you can see that the domain has now become the range. The domain on the exponential has become the range on the logarithm. The range on the exponential has become the domain on the logarithm, simply because those x's and y's have switched. So let's confirm that with this example. So I'm just going to split her up. So we have a 1/4 to the power of x, and we have a log base 1/4 of x. So we'll identify all of our key things: our x-intercept, our y-intercept, our end behavior, our domain, and our range. So our x-intercept, well, there's no x-intercept. Y-intercept, it's still crossing through 1. And behavior, it's going from quadrant 2 to quadrant 1. Domain, well, it's going left, it's going right. It's all real numbers. and our range, it's y's that are greater than or equal to 0, because it's basically kind of starting at the x-axis, going up to read our range. So if we do those same characteristics for our logarithm, we'll see our patterns come to light. So first off, x-intercept. Well, our x-intercept is 1. Our y-intercept, this is going to keep on going up, but it's never going to cross our y-axis. There is no y-intercept. If we're reading this one, though, it's actually starting in quadrant 1. If we're read from left to right, it starts up in quadrant 1 and it ends down in quadrant 4. Our domain, well, it's starting at our y-axis and going to the right, which means it's only our x's that are greater than 0. Our range, our y's that are an element of the real number. Because that arrow means it's going up, that arrow means it's going down, it's hitting every single possible y value. Just like here, you'll see that the y-intercept on the exponential is the x-intercept on the logarithm. Likewise, the x-intercept, which there is none, means that there's no y-intercept. The characteristics of domain and range also switch. Now all of this is for kind of base functions. You see that there's no numbers in front of either of them. But here's one more thing you need to note. If we're looking at this exponential, this is an increasing exponential. On the logarithmic side, it's also increasing, because if we're reading from left to right, it's still getting bigger and bigger. This characteristic does not change. On the exponential, this is a decreasing exponential. If we look at the logarithm, the red, reading from left to right, it is still also decreasing. So whether something is an increasing or a decreasing function, exponential or log, because increasing or decreasing does not talk about x's or y's. It is simply the same kind of characteristic, but you'll notice that the end behavior, where it starts and where it ends, does change. An increasing logarithm starts in quadrant 4 and ends in quadrant 1. A decreasing logarithm starts in quadrant 1 and ends in quadrant 4. So let's do some more work. We're going to use our graphing technology. Again, if you're working on this at home, your graphing technology, Desmos is a great thing to use. It's pretty easy to use, pretty easy to work with. But we're going to do some special things here. So if we graph these logarithms, now each of these logarithms on most technology is very difficult to change. If there's no base, every single one of these logarithms actually has a base 10. And you'll notice with our base being 2 here, which is bigger than 1, it means that we're going to have an increasing logarithm. This base of 1/4 means it's going to be a decreasing logarithm. On the back side, we're going to use that graphic technology to see one more thing with that. So automatically, we should be able to see that this is going to be an increasing logarithm. This 15 is actually going to guarantee it. By putting it into our graphing calculator or using Desmos, we'll see that the graph actually looks something like that. It may not be perfectly like that, but it absolutely works. Even this one has base 10. But this is a little bit different. In pre-calc 30, we do some things about reflections. Well, this is actually going to be a decreasing logarithm. And if you're looking at it, there's only one thing that's different. It's this number in front. Now, the number in front for a logarithm is different than that a value that's in front of a exponential. It's no longer going to be your, on the exponential, it was the y-intercept. For logarithms, it's not going to be your x-intercept. It is simply going to tell you whether it's going to be increasing or decreasing. We still usually notate it as an a value. But if you have already put these into your calculator, you'll see that yes, this is an increasing graph and this is a decreasing graph. If the a value is greater than, or basically greater than 0, we're going to have an increasing logarithm. If the a value is less than 0, it'd be a decreasing logarithm. So if we go into the next two, we'll see that there's some more things to it. You'll once again see something slightly different. This ln. Now ln represents the natural log. In basic use of it, it really just means that it's a log with base e. Instead of the standard log, which has base 10, a ln, yeah, it actually sounds like ln. It's just a log with base e. So it's really no different. At the same time, e, again, remembering, is 2.718284. 495 or something like that. Well, it's bigger than 1, which means it should naturally be a increasing logarithm. Well, what's going to change it is that number in front. That number in front is your a value, which means we'd have a negative ln, and I'm just doing a sketch, and a positive ln. You'll notice in each and every single one of these, there is only one x-intercept. The x-intercept is 1. The y-intercept, well, there's none. Our end behavior is different, though. On our increasing logarithmics, all of them are going from quadrant 4 to quadrant 1. Sorry, just to make that a lot easier to read, put it down there. Whereas on our decreasing logarithms, they're going from quadrant 1 to quadrant 4. Quadrant 1 to quadrant 4. Each and every single one of these domains is all the x's that are greater than 0. But our ranges are all the y's that are all real numbers. Every single one of these share all of those same characteristics. The only difference being that end behavior, just like we had seen on the first page. And since we have a focus on being able to match equations and deal with their characteristics, we're going to do that. And we're going to, of course, provide our reasoning. Now you'll notice here, I've also changed things. I've introduced exponentials and logarithms together. So first off, we're going to look at a few different things. Obviously, it's going to be really nice and easy to identify logarithms. They have a log or the natural logarithm, which is the ln. Exponentials are in the form a c to the power of x. So we're going to match these graphs with our equations and help identify our reasoning. First off, this one. We see we're going from quadrant 1 to quadrant 4. So because it's going from quadrant 1 to quadrant 4, it means we're dealing with a logarithm. More specifically, we're dealing with a decreasing logarithm. The only decreasing logarithm that we have is this equation. Here, we are going from quadrant 2 to quadrant 1, which means we have an increasing exponential. I'm just going to move that over a little bit. And because we have an increasing exponential, we can also somewhat read what our y-intercept is. It looks like it is 5. So which of our equations has a y-intercept of 5? Well, there it is. Increasing exponential, well, our c value is 2. That's identifying all of our key aspects. Our a value is our y-intercept, which is 5. Well, there's 1. C, right here. We are going from quadrant 4 up to quadrant 1, which means we have an increasing logarithm. Sorry, should I have identified that it's decreasing because of the -2. An increasing logarithm because this is a +6. Now, of course, you don't have to write the +6, but it doesn't hurt. And like I had said before, do not say, oh, process of elimination, this is just going to be 2. No, provide your reasoning. We can see from the equation, our y-intercept is going to have to be 2. And because our base is in between 0 and 1, it's going to have to be decreasing. Is that the exact same characteristics as what's here? Our y-intercept is 2. Sorry, y equals 2. Because the a value is 2. And it is a decreasing exponential. How do we know it's an exponential? It's going from quadrant 2 to quadrant 1. how do we match that equation to a decreasing exponential? Because our base of c is 0.1. Go have fun.